Imagine a bank that lends out a fixed number of identical coins. The bank knows exactly how many coins exist, and it also knows the maximum amount each customer might ever ask for. The banker's algorithm works in the same way for computer resources like printers, memory blocks, or CPU cores. The main ideas are: finite resource types. There are m different kinds of resources R1, R2 through Rm. Each kind has a fixed total number of identical units, just like a bag that contains 10 red marbles, 5 blue marbles, etc. Multiple processes. There are n processes P1 through Pn that run programs. Each process can ask for several units of each resource, just like a child can ask for several toys. No preemption. Once a process gets a resource unit, the system will not take it away forcibly. It is like the bank not taking back money that has already been handed out. Maximum claim must be known in advance. Every process must tell the system the biggest number of each resource it might ever need, its maximum demand. This is similar to a customer signing a contract that says, "I will never borrow more than 3 coins at a time." Resources are reusable. After a process finishes, it gives its resources back, just like a child returns the toys after playing. These assumptions let the algorithm reason about the future and decide whether a new request could ever lead to a deadlock, a situation where everybody is waiting for each other forever. Available vector: how many units of each resource are free right now? Real-world picture: the crayons left in the supply box. Max matrix: for every process I, the maximum number of each resource it may ever need. Real-world picture: a list on the wall that says Alice may need up to 2 red, 1 blue crayons. Allocation matrix: how many units of each resource each process currently holds. Real-world picture: the crayons each child is currently holding. Need matrix: how many more units each process still needs to reach its maximum. Computed as need: ij equals max ij minus allocation ij. Real-world picture: the gap between what a child has and what they said they might eventually need. Mathematically, if we have n processes and m resource types, available is a 1 by m vector. Available equals a 1, a 2, up to a m. Max is an n by m matrix. Max of ij equals the maximum demand of process I for resource j. Allocation is an n by m matrix. Allocation of ij equals currently allocated units. Need is derived. Need equals max minus allocation. Having these 4 structures lets the bank, the operating system, answer questions like, can we give 2 more red crayons to Bob, by looking at need and available. Child analogy: the teacher looks at the list of how many crayons each child still wants, need, and compares it with the crayons left in the box, available, before handing out more. Safety check procedure: safety algorithm. The safety algorithm is like a game of who can finish first without getting stuck. The goal is to see if there is any order of processes, a safe sequence, that lets every process finish and return its resources. The step-by-step description. Step 1: work equals available. Make a copy of the free resources. Think of it as a temporary pile of crayons that we can hand out while we test the order. Step 2: finish sub I equals false for all I nobody has finished yet. Step 3: search for a process I such that finish sub I equals false and need sub I less than or equal to work. For every resource type, the needed units are less than or equal to what we have in work. If you find such a process, it means I could complete right now. Step 4: pretend I finishes. Work equals work plus allocation sub I. The process returns all its resources to the pool, just like a child puts crayons back after drawing. Finish sub I equals true. Step 5: repeat steps 3 and 4 until either all finish sub I become true. The system is safe and the order we chose is a safe sequence. Or no such process can be found, the system is unsafe. A deadlock could happen if we grant more resources. Analogy for kids. Imagine a stack of toys on a table called work. Children line up. If a child only needs toys that are already on the table, they can play, then put their toys back, adding more toys to the table for the next child. If at some point no child can play because they all need toys that are not on the table, the game is stuck. That would be unsafe. Mathematically, the algorithm runs in at most n iterations, each checking at most m resource comparisons, giving a time complexity of big O of n times m for the inner loop and big O of n squared times m overall, because the outer loop may repeat up to n times. 4. Resource request evaluation and grant decision process. When a process or child asks for more resources, the system does not give them out blindly. It follows a two-step test that uses the safety algorithm. Step 1: Basic feasibility checks. Request less than or equal to need. The process cannot ask for more than it claimed it might ever need. If a child asks for 5 crayons but said he will never need more than 3, the request is denied. Request less than or equal to available. The system must have enough free units right now. If the box only has 2 red crayons left and the child asks for 3, the request must wait. Step 2: Pretend and test. Temporarily allocate the requested resources. Available prime equals available minus request. Allocation prime equals allocation plus request. Need prime equals need minus request. Run the safety algorithm on the temporary state available prime, allocation prime, need prime. A decision: if the temporary state is safe, the request is granted for real, the temporary values become permanent. If the temporary state is unsafe, the request is denied or made to wait. The process must hold on to what it already has and try later. Real-world analogy: a bank clerk checks a loan application. First, the clerk verifies the borrower does not ask for more money than the contract allows, and that the bank has cash on hand. Then the clerk pretends to give the money and checks whether all other customers could still be repaid later. If the pretend step shows a risk of the bank running out of cash, the loan is not approved. Mathematical expression of the check. If request less than or equal to need and request less than or equal to available, then simulate allocation available prime equals available minus request, allocation prime equals allocation plus request, need prime equals need minus request. If safety check of available prime, allocation prime, need prime equals true, then grant request, else deny request. Process must wait, else deny request, illegal request. Resource totals: A equals 10, B equals 5, C equals 7. Current system snapshot numbers are units. Available equals 332. Max matrix maximum demand. Allocation matrix currently held. Need equals max minus allocation. Process 0 maximum demand 753. Allocation 010. Need 743. Process 1 maximum demand 322. Allocation 200. Need 122. Process 2 maximum demand 902. Allocation 302. Need 600. Process 3 maximum demand 222. Allocation 211. Need 011. Process 4 maximum demand 433. Allocation 002. Need 431. Safety algorithm walkthrough. Step 1: Work equals available equals 332. All finish equals false. Step 2: Look for a process whose need is less than or equal to work. Process 1 needs 122, which fits inside work 332. Choose process 1. Step 3: Simulate process 1 finishing. Work becomes work plus allocation of process 1, which is 332 plus 200 equals 532. Finish of process 1 equals true. Step 4: Repeat search. Process 3 needs 0, 1, 1, which is less than or equal to work 532, so choose process 3. Work becomes work plus allocation of process 3, which is 532 plus 2, 1, 1 equals 743. Finish of process 3 equals true. Step 5: Next, process 4 needs 4, 3, 1, which is less than or equal to work 743, so choose process 4. Work becomes work plus allocation of process 4, which is 743 plus 002 equals 745. Finish of process 4 equals true. Step 6: Next, process 0 needs 743, which is less than or equal to work 745, so choose process 0. Work becomes work plus allocation of process 0, which is 745 plus 010 equals 755. Finish of process 0 equals true. Step 7: Finally, process 2 needs 600, which is less than or equal to work 755, so choose process 2. Work becomes work plus allocation of process 2, which is 755 plus 302 equals 1057. Finish of process 2 equals true. All processes are finished, therefore the system is safe. Safe sequence: 1 possible order. Process 1, process 3, process 4, process 0, process 2. If a new request comes, for example, process 0 asks for 020, we would check request less than or equal to need. Process 0 still needs 743, so okay. Check request less than or equal to available. Available is 332, so okay. Pretend allocation and run safety again. If the algorithm still finds a safe sequence, we grant the request. Time complexity. The safety check scans at most n processes each time and may repeat up to n times, doing a comparison of m resource types each scan. Rough formula: big O of n squared times m. A single request also needs the two simple checks: request less than or equal to need and request less than or equal to available, which are big O of m. So the total cost of handling a request is big O of n squared times m in the worst case. Space complexity. The algorithm stores 4 tables: available size m, max, allocation, need each n times m, so big O of n times m memory. Practical limitations. All maximum demands must be known in advance. In many real programs, the maximum need is not known or changes dynamically, making it hard to use the algorithm. Overhead for many processes. With dozens or hundreds of processes, the big O of n squared times m safety test can become a noticeable delay, especially in a real-time operating system where decisions must be made quickly. No preemption. The model assumes resources cannot be taken away once allocated. Modern systems sometimes preempt, force a process to release resources, which the classic banker's algorithm does not handle. Static resource types. The algorithm works only with a fixed set of resource categories. If new resource types appear at runtime, for example a newly attached device, the tables must be rebuilt. Potential for denial of safe requests. Because the algorithm is conservative, it may refuse a request that would actually be fine, just because it cannot guarantee safety without full knowledge. Rarely used in modern operating system kernels. Most operating systems use simpler deadlock avoidance or detection techniques, like lock ordering or wait for graphs, because they are cheaper and do not require the strict assumptions of the banker's algorithm. Bottom line analogies. The banker's algorithm is like a meticulous bank clerk who checks every loan against a huge spreadsheet before handing out money. It guarantees that the bank never runs out of cash, but the checking takes time and the clerk needs to know exactly how much each customer might ever borrow. In fast-moving playgrounds where kids grab toys spontaneously, such a careful system is too slow and rigid, which is why many modern playgrounds operating systems use simpler rules.